Okay, let's get started. So we were talking about interference, and we talked about double slit experiment and diffraction grading. So today we will talk about single slit, where you only have one slit, okay? And so in single slit you have one slit, like say so that's the magnified version of a single slit. You have this slit in the middle, and consider that wavefront hits the slit. Okay, we have a plane wavefront. Say that's the wavefront. Okay, that's the wavefront, which is just a representation of light. Okay, we represent light with the wavefront. When light is far away from the source, we represent the light with wavefront. And we talked about Huygens principle last time. Huygens says that when the light hits the single slit, the light goes through the slit. Okay, so let's say what happened. So there is this light hits this gap, and each and every point on that wavefront acts as a source of the light. Okay, so that's the Huygens principle. Huygens principle is, again, each and every point on this wavefront acts as a source of light. So these are all the sources of light. Okay, so let's say we have 1, 2, 3, 4, 5, 6 dots. Okay, 6 sources of light. We could have drawn millions of trillions of sources there, but I'm just drawing 6 here. And these sources will produce their own wavelets or wavefronts. The tiny wavefronts are called wavelets, and those wavelets meet here. We have a screen here. Consider we have a screen somewhere here. So these wavelets, they meet here on the screen, either constructively or destructively. If they meet constructively, you will get bright spots, and if they meet destructively, then you get dark spots. Okay, so let's say these rays meet at the center here. So oops, why it's doing that? Okay, let's turn the volume down. So you see that the rays do not have any path difference. Okay, they are traveling the same length of the path. So in this case, the path difference would be delta L between the rays would be 0. So path difference is 0. Okay, that means they will form a bright spot at the center. So here it will be constructive interference. Okay, now let's consider. So let's consider another path. Say so the rays make some angle, let's say theta, with the central line Okay, so these are another possibility. There are millions of possibilities here. So out of millions of possibilities, let's say this is one possibility, how they meet. And let's say the path difference for these rays, let's consider this is 1. One pairs up with this one. Okay, so let's consider this to be 2. So consider this to be 1, ray 1. It pairs with this ray 2, and let's say this is 3. This pairs with this one, and we have this one. This pairs with this one. This is 5 pairs with 6. Okay, so we have 6 rays. This one pairs with 2 here. 3 pairs with 4 here. Okay, and 5 pairs with 6 here. So consider that the path difference between 1 and 2, and 3 and 4, and 5 and 6. Okay, so the path difference between this one and this one, this 3 and 4, and 5 and 6. Okay, for all the path difference is, let's say, lambda over 2. If the path difference is lambda over 2, then we know that it is the half integer of lambda. That means this would be destructive. So the light rays will meet here, and it will form a dark spot. Okay, so this corresponds to a dark spot. We may have another possibility. So let's talk about the third possibility. So let's say these rays meet at different angle. Okay, oops. So we have that ray, that one. Now this is for a different angle. Okay, that's for a different angle. Different angle. Okay, again, let's say this is 1, 2, 3. That's 2, 3. No. Let's say this is 1, and then this is 3. Sorry, 2. That's 3. That's 4. That's 5. That's 6. So 1 pairs with 2, 3 pairs with 4, 5 pairs with 6. Okay, and then for this one, the pairings will have the path difference of 2 lambda over 2. Okay. Again, this will form the destructive interference because the path difference is lambda over 2 times the integer. Similarly, we may have another option. So we may have a greater angle. So let's say that's the next possibility. Okay, so again, do the same thing. So pair the rays. So one with this one, and then this one with this one, and then this one with down this one. Okay, so you have pairs, and they have the path difference of 3 lambda over 2. Okay, so the path difference here for each of these possibilities is let's say p lambda over 2, and they are forming the destructive interference. Okay, dark fringes. So that's the path difference for all these different possibilities. Now we can see what the path difference is from this side. Okay, so if you look at this side, so we have this single fringe, single slit, and we have, let's say, this ray and that ray. So this one is pairing with this one. So this distance is, let's say, the distance of the slit is a. Okay, that means that this distance would be a over 2, half. So this is halfway, or in the middle point of this slit. So that's a over 2. Okay, and the path difference between 1 and 2 is this distance. Okay, so let's use a different color here. So this distance is the path difference. Okay, so this one travels that much part less than this 2. In other words, this 2 travels that much part more than 1. So that's the path difference. and let's say the rays make angle theta with this middle line, and we can show geometrically that this angle and this angle, they are equal. Okay, so in this triangle, look at this triangle. In this triangle, if I write sine theta would be, this is path difference delta L, so delta L opposite over hypotenuse, which is a over 2. Okay, so delta L is a over 2 sine theta. So that's the path difference, and we also derived the path difference for destructive interference as this one. So for destructive interference, we can write we can write a over 2 sine theta is equal to p lambda over 2, and this angle is the angle formed by these rays. Okay, for first one it's 1, for second one it's 2, so we can just write p, okay, for that. So 2 and 2 cancel, we get sine theta p is p lambda. Okay, and there's a also. So this is the sine of angle formed by the rays with this central line. Okay, so that's the angle. Now if this angle is really small, sometimes we can use something called small angle approximation. For small angle approximation, for small angles, when angles are small, sine theta could be written as theta, and also tan theta could also be written as theta. Okay, this is true for any small angles. So we can write this as, for small angle, this as theta p is equal to p lambda over a. Okay. Now let's say we want to know where exactly is the dark patterns from the central point. Okay, so let's see, how do I move it down? So let's say we want to know, that's the slit. Here's the dark pattern, here's the bright pattern. So I'm going to represent the bright one with this kind of graph. So this so here, let me draw here. So here is a single slit, and here is the screen, and I get the central bright spot here because all the rays are meeting without any path difference. So I get the bright spot here, and then dark spot here, and then bright, dark, bright, dark. So for the bright one, let me write this curve. This represents the peak represents it has high intensity at the center. Okay, and then this is where you have dark fringe. Okay, this is where you have dark fringe. And then you have again bright, and again dark, bright, dark, right there. Okay. So I want to know the angle formed by this dark one, dark fringe, with this central line. Okay. So I want to know this angle, which is that, and I also want to know this distance. How far this dark pattern, the first dark one from the center, or the second one from the center. Okay. So how do I know that? I want to know this distance. Okay, distance from center to the first dark fringe, or distance from center to the second dark fringe, or distance from center to the third dark fringe. Okay, I want to know all these distances. How can I find that? So I have this angle to be theta, and this length is L. Okay, so if you take the tan theta, that would be y over L. That will give me y. So y would be L tan theta. Okay. And again, for small angular approximation, we have y is equal to L theta. Okay. L times theta. So, and then we have theta already derived from here. Okay. So for different dark patterns, we can use P here for subscript. So P would be 1, 2, 3, and so on. You can even include 0 also. 0 would be for the middle one, or there's no 0. Okay, so for this one, there's no 0 because the center one is the bright one. So we only have one. We start this from 1 because the center one doesn't form the dark pattern. Okay. So we have theta, which is P lambda over A. Okay. So this formula gives me the distance of the dark patterns from the center. So I can write this as yp is equal to P lambda L over A. If you want to find the angle is given by this. Theta P is P lambda over A. And if you want to find the distance from the center, you use that. So you can use either one depending on what you're asked. Okay. So let me draw it again here. So we have central line, and the center is bright fringe. That's the bright fringe. And then we have dark. This is the dark one. P equal to 1, dark 1. And then we have bright again, and the next dark, P equal to 2. And then bright again, next dark, P equal to 3. We are talking about the dark fringes, okay, here. So angle, this angle for 1 is theta 1, angle for the second one is theta 2, and angle for third one is theta 3, and so on. Okay, so these angles are given by that formula. Whereas this distance is y1, sorry, not that. This distance is y1, that distance is y2, and then other ones also. Okay, so that's given by that. So let's look at a problem from the worksheet. So here is the problem. So you pass a laser light through a narrow slit of width 0.3 millimeter. Let's see if I can put that in that thing. Give me a second. Okay, that's our question. So that's the single slit, and we have screen here. That's the central line. So the narrow slit has the width of 0.300 millimeters. Okay, so that's 0.300 times 10 to minus 3 meters. And then we see the diffraction pattern 6 meters away from the slit. So that's the distance between the slit and the screen, 6 meters. And the distance on the screen between the center of the first maxima on either side of the central bright fringe is 32 millimeters. So we have this central bright fringe, and then dark one, and then bright, dark, bright, dark. Okay. So that's the first dark one. And it says that the distance between the center and the first dark one, Y1, is 32 millimeters, which is 32 times 10 to minus 3 meter. And then we need to find the wavelength of the laser. Lambda is what? So we know for the dark fringe, the distance is given by, again, this is the first one, or the general formula would be Yp is P lambda L over A. And then we want to find lambda. So Y1 is, P is 1. The first one would be, P would be 1. L is 6 meter. Okay, A is 6 meter. 0.3 times 10 to negative 3 meters. And then you plug in the value of y here. Y is 32 times 10 to negative 3. Okay, so solve that and find lambda. That gives you the value of lambda. Again, the basic idea here is to get the condition for this one. Okay, first minima. We are talking about the minima, which is dark fringe. Okay, this is that. Okay, let's look at the next one. So the next one is talking about the limiting angle of resolution. Okay, so for that we need to talk a little bit about the circular aperture. So just like the single slit, if you pass the light or laser through a circular aperture, this is not a slit, this is a circular, a tiny circular hole. Okay, so if you pass light through that, so instead of getting a central spot here, circular spot, you get this concentric spherical pattern. Okay, so you have this central bright spot here, and then dark, bright, dark, like that. And I will not show how we get this one, but we can find the angle of the first dark one. Okay, this is the first dark one, so that means the angle formed by this first dark one with the central line. Okay, this line. So that angle is given by that formula. So that's 1.22 times lambda over d. D is the diameter of that hole, tiny hole. Okay, and then we can also find, knowing that, we can also find the y. So I can also find y, which is this distance, okay, y1. So y1 would be L tan theta 1, and for small angle it would be L theta 1, and that would be L theta is that. Okay, so I get 1.22 lambda L over D. Okay, so why is that? So this is the distance between the central line and the first dark circle, or in other words, from this point, let's see if I can use a different color here. So from here to that, okay, that's y1, which is that. Now, if I want to know the width of this bright spot, then I just need to add the same distance on both sides. Okay, so we have this y1 here, and then we also have y1 here. So the width of this central bright spot is approximately, I shouldn't say it's exactly, but approximately equal to 2 times y1. Okay, y1 on this one side and y1 on the other side. So adding that, you get 2 times y1, which is that. So this gives the width of this central spot. So that's something that you see when you have only one source here, okay, one source of light. Now if you have 2 sources instead of 1, you will see 2 spots, okay, like this. So you have one source of light here, other source of light there, then you get 2 sources there. It's same kind of phenomenon that happens in our eyes also. When we see multiple light sources, like in this case, we have headlights from a car. Okay, as you go far away from the car, or as the car goes far away from you, the light images get closer and closer. And at some point, they overlap. Okay? And then you cannot resolve the light into 2. So it becomes a single image. It's not possible to resolve. So there is a criteria for the distinction of the image, which is called Relics Criteria. Okay, so according to Relics Criteria, so 2-point objects are just resolved when the first dark fringe in the diffraction pattern of 1. So let's say this is the intensity of the first one. Okay. Again, I showed you in the previous picture that we can represent the fringes by this kind of pattern. Okay, so the fringe can be represented by this kind of pattern. So this means this is the bright one, this means that's the dark one. Okay, so this is the pattern for this first one, first image, and this is the pattern for the second one. Okay. Now this Rayleigh criteria says that if the first dark of this one overlaps, this is the dark of this one, okay? If the dark of this one overlaps the bright of this one, then that would still give you the 2 images. Okay, that's the minimum criteria to get the 2 distinct images. If they get closer, let's say if they're closer like that, now this minimum doesn't fall under that. Okay, that means you cannot distinct the 2 objects in this case. Okay, you can resolve the 2 objects only if this dark one falls on the bright of the other one. Okay, or farther from each other. If they are farther from each other, or at least like they have overlapping of bright and dark, then you get the distinct image. If they are too close like that, then you don't see the distinct images. So this is the criteria for the resolution of the minimum criteria for the resolution of 2 objects. Okay, this is the formula that we will be using for next problem. In order to see two objects distinctly, you need that criteria. Okay, so let's see the problem. So this is asking to find the limiting angle of resolution for the microscope. So can you guys try that? So the criteria is theta minimum is 1.22 lambda over d. Okay. That's the limiting angle for resolution of the microscope. So 1.22 lambda is that, okay, 589 nanometers, and d is diameter, which is 0.90 centimeters. You need to convert this to meter and this one also to meter, and that will give you the limiting angle. This one is exactly same kind of question, but this is for the visible light. Okay, so you have 7 different colors for visible light. You have R, O, Y, G, B, I, V. You can choose any of these colors, okay, and then use the lambda for that. So you can Google the wavelength of yellow color or green color and use the lambda for that, and that will give you theta minimum. Okay, that's what it says. So you can use any wavelength you desire, but that should be within the visible spectrum. So use one of the colors. And when you are finding theta, you should get the answer in radian. So the unit for, again, the angle here is radian, not degrees. Okay. Okay, so that's the end of this chapter. Now the next chapter is ray optics, which is much easier than these chapters. Okay. So ray optics is basically, we, instead of using the wave fronts, we use rays. Okay, so here we have wave fronts. So we used wave fronts. But now we will be representing the light with rays, or a light with a line with an arrow. So we have wavefront. So instead of using that, we'll be using this line that is perpendicular to these wavefronts. Okay, and that's the ray. So we represent light by a straight line with an arrow, which is called ray. And the rays are always perpendicular to the wavefronts. Okay? So if you want to draw a ray here, then this ray needs to be perpendicular to each and every point here. So that would be the ray, okay? Because this is perpendicular to each and every point. If you want to draw a ray here, then the ray needs to be perpendicular to each and every point. You cannot draw like that because that's not perpendicular. That's not perpendicular. That's not perpendicular. It needs to be perpendicular. Okay? So you see here, that's perpendicular, that's perpendicular, perpendicular. So you can draw rays that are perpendicular to the wavefronts. So it's easier to represent light with rays because you can solve the problems just by using the geometry, simple geometry. Okay. So for example, we will see example how it is used to solve different kinds of physics problems, optics problems. So let's look at the third problem, third worksheet problem. So it's asking when you stand in front of a mirror, how big the mirror should be to see your full image. Okay? So we can use the ray optics to solve that problem. But before we solve that problem, we need to state three different laws for reflection. Okay? So reflection occurs when light traveling in a medium, let's say the medium is air, hits another medium. So let's say this is another medium. Let's say that's water. Okay? So when the ray hits the boundary between the two media and the light is bounced back in the same medium. Okay? So that's called reflection. So reflection is a phenomena where light traveling in one medium bounces another medium and it's bounced back in the same medium. So there are three laws for reflection. So before we solve this problem, let's state the three laws and then we can talk about the reflection. So the three laws are, let's say, we have a boundary. This is the boundary between two media. This could be a glass and air. So we have air and glass. And light hits the boundary. So when you draw a ray, you need to draw a line with an arrow. Okay. So if you don't write the arrow, that won't be a meaningful drawing. And then it bounces back. And in order to state the law, we need to draw a perpendicular line to the boundary. Okay, so we need to draw a perpendicular line, which we call normal. That doesn't look perpendicular. So let's draw a perpendicular line here. So we call this a normal. Okay. This is called incident light or incident ray. The ray that hits on the boundary, and this is called reflected ray. And the laws of reflection tells us that the angle formed by this incident ray with the normal, this angle called this theta I, this angle of incidence is equal to the angle of reflection, this one, okay, angle formed by reflected ray to the normal. So angle of incidence is theta I, and angle of reflection is theta r. Sorry, I should write theta r here. Okay, they are equal. That's the first law. And again, you need to draw an arrow here. Second law is if you hit the boundary by the light at the perpendicular distance, or I mean direction, then it will be bounced back along the same perpendicular line. Okay? So the ray will be reflected along the same line. So second one is if a ray hits the boundary along the direction of normal, it is reflected along the same direction. Okay, that's the second one. Now the third one is so this incident ray, reflected ray, and normal, they meet at a common point on this surface, reflecting surface. That's the third one. Okay. So reflected ray, normal, and incidental ray meet at a point on the boundary. Okay, so those are the three rules that we need to use to solve the problem. So let's look at the question now. So let's say you have a meter here, okay, and that's the person, and let's draw this line. So that's the height of the person. Let's call that h. And now divide this height into two parts. Let's say the part from the head to the eyes is called it's h1. And from eyes to the feet is, let's call, h2. Okay. Now let's say a ray comes from the feet and then hits the meter. Okay, like that. And then this ray will follow the law of reflection, which is the law of reflection is so that's the normal. Okay, so this angle is angle of incidence. Then the angle formed by the angle of reflection must also be equal to that. That means this drawing is not very good, so we need to draw the normal halfway between the eye and the feet, so somewhere here. Okay, so that's the incident light, and that's the reflected light. Okay, so that means this distance, that is half of the whole body, okay, I should say half of h2 over 2. Okay, so from eyes to the feet is h2, and that's half of that, because this normal should be halfway between the eye and the feet. Okay, so that's that. And then in order to see the head, so let's draw the normal halfway between the head and the eyes. So that's the normal. Okay, and then this is the incident light, and then this is the reflected light. Again, this distance, this much is h1/2, half of head to the eyes. Okay, so this is the total length of the mirror you need. Okay, total size of the mirror to see the head and the feet. So the total size here is h1/2 plus h2/2, which is h1 plus h2/2. And then we know that h1 plus h2 is h, okay, over 2. That means size of the mirror is half the size or height of the person. Okay, so you need to use this figure to answer that. Okay. Any question? Okay, let's look at one more and then we are done. So let's look at this problem. So it's asking if a ray hits on the mirror at 65 degrees, what would be the angle formed by this reflected ray on this part of the mirror? So it shouldn't take long. Okay, let's look at this problem. So look at this part, okay, this part. If this is 65 degrees, then this must also be 65 degrees because the angle of incidence is equal to the angle of reflection. So that's 65 degrees. And this is normal, so this is normal. That means that should be 90 degrees. So that means this angle should be 90 minus that angle. Okay, that's 65 degrees, and 90 minus 65 is that angle, which is what, 25 degrees, right? Yeah. And then this is a triangle. The sum of the angles in the triangle, alpha plus phi plus 120 is 180 degrees. Okay, so if you add the angles in this triangle, alpha we just found alpha phi we just found that it's 25 degrees plus 120 degrees is 180 degrees, and then alpha is 180 minus, that's 145, that's 35, is that right? 35, yeah. So this angle is 35 degrees. And then this is 90 degrees. Okay, so this is right angle, so 90 degrees. That means this angle should be 90, the total angle 90 minus that angle, this alpha, which is 55 degrees. And we know that from laws of reflection, this angle must be equal to that angle. If this is 55 degrees, then that also must be 55 degrees. Okay. So that's that. So you can do that. So do up to number 4, okay? Finish up to number 4. We will continue number 5 next time.